based on the questions that I get at office hours and on forum, I just wanted to address the boater and the river problem first. So one thing I wanted to say is that is that there is another mnemonic device for how to transform velocities. I understand that relative motion, it's an uncomfortable topic. So you can, if you have two frames, right, and you have an object moving and you want to describe the motion of that object in two frames, or velocities, or velocity of that object in two frames, right? So O is object, okay? And then you have frames S and S prime, right? So you can say that velocity of the object relative to S is velocity of the object relative to S prime plus velocity of frame S prime relative to S. So in the other way of writing, remember I called this U, I called this U prime, and I called that big V or something. But maybe this is harder to remember, harder to repeat in your mind's eye. And perhaps when you do it like that, when you label things, this is easier, and you can kind of see how the labels here sort of contract, and what you end up with is what you want. So let's apply that to the boater and the river problem, right? So you have the shore, and then you have the river. And let's say, okay, so this is your pier 1, and this is your pier 2. And let's say the boater first is going in this direction. In this problem, and as in any problem, it's a continuous dance or interplay between the math and physical intuition. The key to this problem is that the boater has a rule of the game to play, one single rule. And that one single rule is that whenever the boater looks at the water, steers his head at the water, the speed of the water relative to the boat has to always be v, the speed of the walker, right? So the walker is moving with speed v, okay? And when the boater looks at the water should be moving relative to the boat at that same speed v. So if you think about just the physics, not math, when the boater is going from pier 1 to pier 2, he or she has to outrun the river relative to the shore by speed v, right? So regardless of how fast the water is moving, the boater has to move to the right in the positive x direction with speed v relative to the river, okay? So relative to the shore, the boater will be moving really fast, okay? You can think of this as swept down flow, but it's not really swept down flow. It's just that the boater has to satisfy a certain rule of the game. If the river is going with velocity vr, and the boater's speed relative to the river has to be v, well, then the boater's velocity of the boater relative to the ground has to be the river plus v. Now, how does that, can we apply this directly? Let's try. So velocity of the object is now the boater. Boater relative to the ground equals velocity of the boater relative to the river plus velocity of the river relative to the ground. Let's fill in. So this is, so this is velocity, right? So this is velocity. Now we know speed of the speed of the boater relative to the river is v, okay? And velocity of the boater relative to the river is plus v. The difference between speed and velocity in one dimension is just a matter of a sign, okay? And on the way from pier 1 to pier 2, the boater is going in the positive x direction, even relative to the river, is still going in the positive x direction. So this is just v, and this is vr, right? Again, positive because the river is flowing in the positive x direction. Okay, so that's what we want. Okay, so that's the velocity of the boater relative to the ground. So you can see that I get this answer by physical reasoning or by quote unquote mathematical reasoning. Of course, there are two ways of describing the same thing, but I want to draw your attention to this very important way of thinking of always juxtaposing physical reason with mathematical reason. Okay. Here's another, well, I'll give another example of this. How about on the way back? Okay, so this is 1 to 2, how about 2 to 1? And you know what, I still am very unhappy about this writing pad. I'm gonna try to do something about it. Everything was done in a hurry and they did not have iPads ready. So they gave us Wacom tablets and I'm not happy about it. Okay, so this is 1 to 2, how about 2 to 1? Well, the river is still flowing in this direction. So velocity of the river relative to the ground is positive. Okay. Let's apply. Okay, so this is so this is sort of physical reasoning, and this is the math, right? So this is physics. See, and this is the math. Okay. Okay, so let's just apply the math. I'm going to use this form of the velocity transformation. The velocity of the boater relative to the ground, let's say you didn't see this, equals velocity of the boater relative to the river plus velocity of the river relative to the ground. Okay? Speed of the boater relative to the river is v. The river is moving that way, so when the boater looks at the river, he will say, well, I'm going in the negative x direction relative to the river. Okay? So if the boater doesn't row, his or her velocity relative to the river would be 0. And to get to pier 1, they have to row in the negative x direction, not only relative to the ground, but also relative to the river. So this will now be minus the v. So this is where I'm converting speed to velocity. It's not a big deal. It's not supposed to be so hard. That's what I'm saying. And velocity of the river relative to the ground is still r. Okay, so good. So velocity of the boater relative to the ground is now r minus v. Now, if vr is less than v, as long as the river is flowing slower than the walker, this will be negative, okay? Less than 0 if vr is less than v. And so if we're working with speeds and distances as opposed to velocities and displacements, for speed we'll have to multiply this by -1. So speed, so if then speed is minus v. Okay. Notice, so here comes the physics now. If v equals vr, the speed of the boater relative to the ground is 0. Now, does that make physical sense? Why? Remember, the boater has to satisfy a certain rule of the game. That is, when the boater looks at the water, the speed of the water relative to the boat should be speed of the walker. And if the river is moving with speed v relative to the ground, what is it that the boater has to do in order to satisfy that rule of the game? The boater has to just stay next to pier 2 and just chill, do absolutely nothing. And that will satisfy that rule of the game, okay? They have to anchor themselves to pier 2, and they look at the water and say, oh, look, the water is flowing with speed v relative to me. I'm good. I'm good. So that's the physics now. And that's contained in the smell. Okay? And by the way, how long will it take for the boater to get to pier 1 now? Infinite amount of time, because they're staying next to pier 2. They would never get to pier 1. Okay? So as you're working through problems, I really advise you and want you to continuously go back and forth between, does it make sense physically? What does physics predict? So it goes both ways. Think about physics, you do the math. You've done the math, you go back and check if physics makes sense. That's a mature, very grown-up way to solve problems, any problems, engineering, physics, any technical problems, maybe even non-technical. I wanted to say one other thing. When you find the time of the boater, you have to think whether it's always larger than the time of the walker, you know, back and forth time, or sometimes larger, sometimes smaller. And I'm advising that you take your expression for T boater, okay, you simplify it, and then look at the ratio T boater over T walker. You clean it up, and when you look at that, if you do it right, if you do the algebra right, it will become obvious which one is greater, and if it's always greater, or if it's sometimes greater, sometimes not greater. And I'm giving even a further advice is to plot that ratio versus, for instance, you can plot it versus a V at some fixed VR, or even better, you can plot it versus the ratio of VR over V. And when you look at the plot, it will say so much. So much of the story will be contained in that plot, a lot will become clearer. I will have that in the solutions. The plot is, I don't think it was mandatory, but it's a recommendation. And again, it's part of what makes problem solving mature and grown up. So I will post it in solutions. You will see how that works. I hope this was helpful. So now we will move on with the lecture.